An open delta transformer configuration is a method of creating a three-phase system from a single-phase source by using two transformers connected in a specific way. Let's discuss its operation. On the primary side, two phases, designated A and B, and a neutral conductor from the single-phase source are connected to the primary windings of the transformers. On the secondary side, the secondary windings of the transformers are connected in an open delta configuration, meaning that only two phases, designated C and D, are connected together. The third phase, designated E, is left open. Due to the open delta configuration, the secondary voltages, volt sub C and volt sub D, are 180 degrees out of phase. The third phase voltage, volt sub E, is calculated as the vector sum of volt sub C and volt sub D, which results in a 120-degree phase shift. The open delta transformer connection effectively creates a balanced three-phase system with three equal magnitude voltages, volt sub C, volt sub D, and volt sub E shifted by 120 degrees. However, this three-phase system has only two-thirds of the power capability of a true three-phase system with the same voltage in phase angles. As an example, consider a 12,470 volt single-phase system. Using an open delta transformer configuration, you can create a three-phase system with the following voltages: primary 12,470 volts at a B and 7,200 volts at a N, and secondary 7,200 volts C to D and 12,470 volts C to E. To understand the phase relationships, a vectorial diagram is helpful. Although an open delta transformer configuration can create a three-phase system from a single-phase source, it is important to note that the resulting system has reduced power capability compared to a true three-phase system. It is also essential to consider the vectorial relationships to fully understand the system's behavior. I will now go over the concept of vector groups, transformer polarity, and how to determine these relationships. Vector groups are a shorthand notation used to describe the phase shift between the primary and secondary voltages in three-phase transformers. These groups are defined by international standards like IEC 60076-4 and are crucial for ensuring proper transformer connections and avoiding issues like circulating currents or voltage imbalances. The vector group designation consists of two letters followed by a number. The first letter indicates the primary winding connection, the second letter indicates the secondary winding connection, and the number indicates the phase shift in IRs, where each IR represents 30 degrees. The primary winding connections are typically designated as follows. D for delta connection, where the windings are connected in a closed loop. Y for Y or star connection, where one end of each winding is connected to a common neutral point. And Z for zigzag connection, which is a variation of the Y connection used to improve voltage balance under unbalanced load conditions. The secondary winding connections use lowercase letters with the same meanings: D for delta, Y for Y, and Z for zigzag. The number indicates the phase displacement between the primary and secondary line to neutral voltages. This number is expressed in terms of a clock IR, where each IR represents 30 electrical degrees. For example, a vector group of dinon indicates the following. D, the primary winding is connected in delta. Y, the secondary winding is connected in Y. And 1, the secondary voltage lags the primary voltage by 30 degrees. Common vector groups include dinon, din11, in0, idon, and id11. Each vector group has specific phase relationships that must be considered when paralleling transformers or connecting them to existing systems. Transformer polarity refers to the instantaneous direction of the voltage induced in the secondary winding relative to the primary winding. It is essential for proper transformer connections, especially when paralleling transformers or connecting them in three-phase banks. Transformer polarity is typically indicated by markings on the transformer terminals, such as zone and H2 for the primary windings and zone and X2 for the secondary windings. These markings indicate the relative polarity of the windings. There are two main types of transformer polarity: additive and subtractive. In additive polarity, the voltage between the horn terminal of the primary winding and the zone terminal of the secondary winding is greater than the voltage of either winding alone. This occurs when the hone and zone terminals are on opposite sides of the transformer core. In subtractive polarity, the voltage between the hone terminal of the primary winding and the zone terminal of the secondary winding is less than the voltage of either winding alone. This occurs when the hone and zone terminals are on the same side of the transformer core. Determining the vector group and polarity of a transformer is essential for ensuring proper connections and avoiding issues. The following methods can be used. Nameplate information. The transformer nameplate typically includes the vector group and polarity information. This is the most reliable source of information. Vector group testing. Specialized test equipment can be used to determine the vector group of a transformer. This involves applying voltages to the primary windings and measuring the resulting voltages on the secondary windings. Polarity testing. A simple voltmeter can be used to determine the polarity of a transformer. This involves connecting the hone and zone terminals together and measuring the voltage between the H2 and X2 terminals. If the voltage is greater than the voltage of either winding alone, the transformer has additive polarity. If the voltage is less than the voltage of either winding alone, the transformer has subtractive polarity. Understanding vector groups and transformer polarity is crucial for anyone working with three-phase power systems. By properly identifying and connecting transformers, you can ensure safe and reliable operation. Let's shift gears and discuss transformer nameplates. Transformer nameplates contain a wealth of critical information about the transformer's characteristics and operating parameters. Understanding the information on a transformer nameplate is essential for proper installation, operation, and maintenance. Here's a breakdown of the key information you'll typically find on a transformer nameplate. Firstly, manufacturer information. This includes the name and location of the transformer manufacturer. Secondly, serial number, a unique identifier assigned to the transformer by the manufacturer. Thirdly, kVA rating, the apparent power rating of the transformer in kilovolt amps, indicating the maximum power the transformer can deliver at its rated voltage and frequency. Fourthly, voltage ratings, the primary and secondary voltage ratings of the transformer. For example, 12,470 volts delta to 208Y/120 volts. These values indicate the voltages at which the transformer is designed to operate. Fifthly, current ratings, the primary and secondary current ratings of the transformer in amps. These values indicate the maximum current the transformer can handle at its rated voltage and kVA. Sixthly, frequency rating, the frequency at which the transformer is designed to operate, typically 50 Hz or 60 Hz. Seventhly, impedance, the impedance of the transformer expressed as a percentage. This value is important for calculating short-circuit currents and coordinating protective devices. Eighthly, insulation class, the insulation class of the transformer windings, indicating the maximum operating temperature of the insulation material. Ninthly, winding connections, a diagram showing the connections of the primary and secondary windings. This is important for proper installation and connection of the transformer. Tenthly, vector group. As discussed earlier, the vector group indicates the phase shift between the primary and secondary voltages in three-phase transformers. 11thly, oil capacity for oil-filled transformers, the amount of oil required for proper cooling and insulation. 12thly, weight, the total weight of the transformer, including the core, windings, and enclosure. 13thly, year of manufacture, the year in which the transformer was manufactured. 14thly, standards compliance, a list of the standards to which the transformer complies, such as ANSI, IEE, or IEC standards. By carefully reviewing the information on a transformer nameplate, you can ensure that the transformer is properly installed, operated, and maintained. Now let's explore the concept of transformer taps. Transformer taps are connections in the transformer winding that allow you to adjust the turns ratio and, consequently, the output voltage. Taps are used to compensate for voltage variations in the supply voltage or to adjust the output voltage to meet the specific requirements of the load. Taps are typically expressed as a percentage of the nominal voltage. For example, plus or minus 2.5%, plus or minus 5%. These values indicate the range of voltage adjustment that can be achieved using the taps. There are two main types of transformer taps. Firstly, no-load tap changers, also known as energized tap changers or DECs. These taps can only be adjusted when the transformer is de-energized. They are typically used to make infrequent adjustments to the output voltage. Secondly, unload tap changers, also known as ULTs. These taps can be adjusted while the transformer is energized and under load. They are typically used to make frequent adjustments to the output voltage to compensate for voltage fluctuations. No-load tap changes are typically located inside the transformer tank and are accessed by removing a cover or panel. On-load tap changes are typically located in a separate compartment on the transformer and are equipped with a motor-driven mechanism for adjusting the taps. When selecting transformer taps, it is important to consider the following factors. Firstly, the range of voltage variation in the supply voltage. Secondly, the voltage requirements of the load. Thirdly, the frequency of voltage adjustments. And fourthly, the type of tap changer required, no load or unload. Adjusting transformer taps should only be performed by qualified personnel in accordance with the manufacturer's instructions. Improper tap settings can result in overvoltage or undervoltage conditions which can damage the transformer or the connected equipment. Understanding transformer taps and how to use them is essential for maintaining proper voltage levels in power systems. Now we'll switch to discussing transformer loading and the factors that affect how much load you can safely put on a transformer. Transformer loading refers to the amount of power that a transformer is delivering to its load, typically expressed as a percentage of its rated kVA. Proper transformer loading is essential for ensuring reliable operation and prolonging the life of the transformer. Overloading a transformer can lead to overheating, insulation breakdown, and ultimately transformer failure. Several factors affect transformer loading capability. Firstly, ambient temperature. The ambient temperature around a transformer affects its ability to dissipate heat. High ambient temperatures reduce the transformer's loading capability. Secondly, altitude. Transformers installed at higher altitudes have reduced loading capability due to the low density of air, which reduces cooling effectiveness. Thirdly, cooling method. The type of cooling system used in the transformer affects its loading capability. Transformers with forced air or forced oil cooling can handle higher loads than those with self-cooled systems. Fourthly, voltage and frequency. Operating the transformer at voltages or frequencies outside of its rated values can reduce its loading capability. Fifthly, harmonic content. Harmonic currents in the load can increase transformer heating and reduce its loading capability. Sixthly, load type. The type of load connected to the transformer affects its loading capability. Nonlinear loads, such as those found in electronic equipment, can generate harmonic currents that increase transformer heating. To determine the appropriate transformer loading, you should consider the following steps. Firstly, determine the transformer's rated kVA from the nameplate. Secondly, calculate the actual load on the transformer in kVA. Thirdly, apply any directing factors based on ambient temperature, altitude, or harmonic content. And fourthly, compare the actual load to the rated kVA rating of the transformer. It is generally recommended to keep the transformer loading below 80% of its rated kVA to provide a safety margin and prolong the life of the transformer. Monitoring transformer temperature is also important for ensuring proper loading. Many transformers are equipped with temperature sensors that can be used to monitor winding and oil temperatures. Exceeding the transformer's temperature limits can indicate overloading or a cooling system problem. Proper transformer loading is essential for ensuring reliable operation and prolonging the life of the transformer. By carefully considering the factors that affect transformer loading capability and following the recommended loading guidelines, you can avoid overloading the transformer and prevent costly failures. Let's talk about transformer maintenance, which is crucial for ensuring reliable operation and prolonging the life of the transformer. Regular maintenance can help identify and address potential problems before they lead to costly failures. Here are some key aspects of transformer maintenance. Firstly, visual inspection. Regularly inspect the transformer for any signs of damage, such as oil leaks, cracked bushings, or corroded connections. Secondly, oil level. For oil-filled transformers, check the oil level regularly to ensure that it is within the proper range. Low oil levels can indicate a leak or other problem. Thirdly, oil quality. Regularly test the transformer oil to ensure that it is free from contaminants and has the proper dielectric strength. Contaminated or degraded oil can reduce the transformer's insulation capability. Fourthly, temperature monitoring. Monitor the transformer's winding and oil temperatures regularly to ensure that they are within the proper range. Overheating can indicate overloading or a cooling system problem. Fifthly, bushing inspection. Inspect the transformer bushings for any signs of cracking, chipping, or contamination. Damaged or contaminated bushings can lead to flashovers and transformer failure. Sixthly, connection tightness. Check the tightness of all electrical connections in the transformer to ensure that they are secure. Loose connections can cause overheating and voltage drops. Seventhly, tap changer maintenance. For transformers with on-load tap changers, regularly inspect and maintain the tap changer mechanism to ensure that it is operating properly. Eighthly, cooling system maintenance. For transformers with forced air or forced oil cooling, regularly inspect and maintain the cooling system components, such as fans, pumps, and radiators. Ninthly, insulation resistance testing. Perform insulation resistance tests, also known as mega tests, on the transformer windings periodically to assess the condition of the insulation. Tenthly, turns ratio testing. Perform turns ratio tests on the transformer to verify that the turns ratio is within the proper range. 11thly, dissolved gas analysis. For oil-filled transformers, perform dissolved gas analysis, or DGA, on the transformer oil periodically to detect any signs of internal faults. DGA can help identify problems such as overheating, arcing, or corona discharge. Transformer maintenance should be performed by qualified personnel in accordance with the manufacturer's instructions and applicable standards. A well-maintained transformer will provide years of reliable service. Now, let's delve into transformer protection, which is essential for safeguarding transformers from damage caused by overcurrents, overvoltages, and other abnormal conditions. Proper protection can prevent costly failures and ensure the reliability of the power system. Here are some common transformer protection methods. Firstly, overcurrent protection. Overcurrent protection devices, such as fuses and circuit breakers, are used to protect the transformer from overcurrents caused by faults or overloads. These devices are typically installed on both the primary and secondary sides of the transformer. Secondly, differential protection. Differential protection is a sophisticated protection method that compares the currents entering and leaving the transformer. If there is a significant difference between the currents, it indicates an internal fault, and the protection system will trip the transformer. Thirdly, overvoltage protection. Overvoltage protection devices, such as surge arresters, are used to protect the transformer from overvoltages caused by lightning strikes or switching surges. These devices are typically installed on the primary side of the transformer. Fourthly, restricted earth fault protection. Restricted earth fault, or REF, protection is used to detect earth faults in the transformer windings. This protection method is particularly effective for detecting low-level earth faults that may not be detected by overcurrent protection. Fifthly, temperature monitoring. As mentioned earlier, temperature monitoring is an important aspect of transformer protection. High winding or oil temperatures can indicate overloading or a cooling system problem, and the protection system can trip the transformer if temperature limits are exceeded. Sixthly, pressure relief devices. Pressure relief devices are used to protect the transformer from overpressure caused by internal faults. These devices are designed to vent the pressure and prevent the transformer tank from rupturing. Seventhly, Buchholz relay. The Buchholz relay is a gas-actuated relay used on oil-filled transformers to detect internal faults. The relay detects the accumulation of gas in the transformer tank, which is a sign of an internal fault, and trips the transformer. The selection and coordination of transformer protection devices should be based on a thorough analysis of the power system and the transformer's characteristics. Protection settings should be carefully selected to provide adequate protection without causing nuisance tripping. Regular testing and maintenance of transformer protection systems are essential for ensuring their proper operation. Now let's discuss transformer efficiency, a critical parameter that reflects how effectively a transformer converts electrical power from one voltage level to another. A higher efficiency means less energy is lost as heat, resulting in lower operating costs and reduced environmental impacts. Transformer efficiency is defined as the ratio of output power to input power, expressed as a percentage. Efficiency equals output power divided by input power times 100%. Transformer losses are the primary factor that affects efficiency. These losses can be divided into two main categories. Firstly, coal losses, also known as iron losses. These losses are caused by the alternating magnetic field in the transformer core and are independent of the load. Coal losses consist of hysteresis losses, which are caused by the energy required to repeatedly magnetize and demagnetize the core material, and eddy current losses, which are caused by circulating currents induced in the core material by the alternating magnetic field. Secondly, winding losses, also known as copper losses. These losses are caused by the flow of current through the transformer windings and are proportional to the square of the current. Winding losses depend on the resistance of the windings and the load current. Transformer efficiency typically varies with load. Efficiency is generally highest at or near the transformer's rated load and decreases at lighter loads due to the constant core losses. Several factors affect transformer efficiency. Firstly, transformer design. The design of the transformer, including the core material, winding material, and construction techniques, significantly affects its efficiency. Secondly, transformer size. Larger transformers tend to be more efficient than smaller transformers due to the lower ratio of surface area to volume, which reduces heat dissipation. Thirdly, load level. As mentioned earlier, transformer efficiency varies with load. Efficiency is generally highest at or near the transformer's rated load. Fourthly, operating voltage and frequency. Operating the transformer at its rated voltage and frequency maximizes its efficiency. Fifthly, ambient temperature. Higher ambient temperatures can increase transformer losses and reduce its efficiency. To improve transformer efficiency, consider the following measures. Firstly, use high-efficiency transformers. Select transformers that are designed for high efficiency, with low core losses and winding losses. Secondly, optimize transformer loading. Operate transformers at or near their rated load to maximize efficiency. Thirdly, reduce harmonic content. Minimize harmonic currents in the load to reduce transformer heating and losses. Fourthly, improve cooling. Ensure that transformers are adequately cooled to reduce operating temperatures and losses. Fifthly, regular maintenance. Perform regular maintenance to ensure that the transformer is operating at its peak efficiency. Understanding transformer efficiency and the factors that affect it is essential for optimizing power system performance and reducing energy consumption. Now let's discuss some common transformer problems, which can range from minor issues to major failures. Identifying and addressing these problems promptly can prevent costly repairs and downtime. Here are some common transformer problems. Firstly, overheating. Overheating is one of the most common transformer problems. It can be caused by overloading, inadequate cooling, high ambient temperatures, or harmonic currents. Overheating can lead to insulation breakdown and transformer failure. Secondly, oil leaks. Oil leaks are a common problem in oil-filled transformers. They can be caused by damaged gaskets, corroded tanks, or overpressure. Oil leaks can lead to low oil levels, which can reduce the transformer's cooling capability and insulation strength. Thirdly, insulation failure. Insulation failure can be caused by overheating, overvoltages, contamination, or aging. Insulation failure can lead to short circuits and transformer failure. Fourthly, bushing failure. Bushing failure can be caused by cracking, chipping, contamination, or overvoltages. Damaged or contaminated bushings can lead to flashovers and transformer failure. Fifthly, tap changer problems. Tap changer problems can be caused by mechanical wear, corrosion, or electrical faults. Tap changer problems can lead to voltage regulation issues and transformer failure. Sixthly, winding faults. Winding faults can be caused by insulation failure, overcurrents, or mechanical stress. Winding faults can lead to short circuits and transformer failure. Seventhly, core problems. Core problems can be caused by insulation failure, overcurrents, or mechanical stress. Winding faults can lead to short circuits and transformer failure. Eighthly, core problems. Core problems can be caused by insulation failure, loose laminations, or core saturation. Core problems can lead to increased core losses and transformer overheating. Ninthly, noise and vibration. Excessive noise and vibration can be caused by loose core laminations, mechanical resonance, or electrical faults. Noise and vibration can be a sign of a serious transformer problem. Tenthly, corrosion. Corrosion can occur on transformer tanks, bushings, and connections. Corrosion can weaken the transformer's structure and lead to leaks or electrical faults. To prevent transformer problems, it is important to perform regular maintenance, monitor transformer operating conditions, and address any issues promptly. If you suspect a transformer problem, it is important to consult with a qualified electrician or transformer specialist. I will now touch on transformer installation best practices. Proper transformer installation is crucial for ensuring reliable operation and prolonging the life of the transformer. Here are some best practices for transformer installation. Firstly, site selection. Choose a suitable location for the transformer that is clean, dry, well ventilated, and accessible for maintenance. Secondly, foundation. Provide a solid and level foundation for the transformer to prevent vibration and stress on the transformer tank. Thirdly, clearances. Maintain adequate clearances around the transformer to allow for proper ventilation and access for maintenance. Refer to the manufacturer's recommendations and applicable codes for clearance requirements. Fourthly, grounding. Properly ground the transformer to protect against electrical shock and prevent damage from lightning strikes or other overvoltage events. Fifthly, connections. Make all electrical connections to the transformer in accordance with applicable codes and standards. Ensure that all connections are clean, tight, and properly insulated. Sixthly, oil filling. For oil-filled transformers, fill the transformer with the proper type and amount of oil in accordance with the manufacturer's instructions. Seventhly, testing. Perform all necessary tests on the transformer after installation, such as insulation resistance tests, turns ratio tests, and polarity checks. Eighthly, protection. Install appropriate overcurrent and overvoltage protection devices to protect the transformer from faults and abnormal conditions. Ninthly, labeling. Clearly label all transformer terminals, connections, and controls to facilitate proper operation and maintenance. Tenthly, documentation. Maintain accurate records of all transformer installation activities, including test results, connection diagrams, and equipment settings. Transformer installation should be performed by qualified personnel in accordance with applicable codes, standards, and manufacturer's instructions. I will now briefly cover the topic of autotransformers. An autotransformer is a type of transformer that uses only one winding to serve as both the primary and secondary windings. Unlike traditional transformers, which have separate primary and secondary windings that are electrically isolated from each other, an autotransformer has a single winding that is tapped at different points to provide different voltage levels. In an autotransformer, a portion of the winding is common to both the primary and secondary circuits. The primary voltage is applied across the entire winding, while the secondary voltage is taken from a tap on the winding. The voltage ratio of an autotransformer is determined by the ratio of the number of turns between the input and output taps. Autotransformers offer several advantages over traditional transformers. Firstly, smaller size and weight. Autotransformers are typically smaller and lighter than traditional transformers of the same kVA rating. Secondly, higher efficiency. Autotransformers generally have higher efficiency than traditional transformers due to the reduced amount of copper and iron used in their construction. Thirdly, lower impedance. Autotransformers have lower impedance than traditional transformers, which can improve voltage regulation. Fourthly, low cost. Autotransformers are typically less expensive than traditional transformers of the same kVA rating. However, autotransformers also have some disadvantages. Firstly, no electrical isolation. Autotransformers do not provide electrical isolation between the primary and secondary circuits, which can be a safety concern in some applications. Secondly, fault current. Autotransformers can have higher fault currents than traditional transformers, which may require larger overcurrent protection devices. Autotransformers are commonly used in applications where electrical isolation is not required and where size, weight, efficiency, and cost are important considerations. Some common applications of autotransformers include voltage regulation, motor starting, and power transmission. Understanding the principles and applications of autotransformers is essential for electrical engineers and technicians. Finally, let's delve into three-phase transformer connections. Three-phase transformers are used to transform voltage levels in three-phase power systems. These transformers can be connected in various configurations, each with its own advantages and disadvantages. The most common three-phase transformer connections are firstly, delta-delta connection. In a delta-delta connection, both the primary and secondary windings are connected in a delta configuration. This connection is commonly used for industrial loads and provides good voltage regulation. However, it does not provide a neutral point for single-phase loads. Secondly, delta-Y connection. In a delta-Y connection, the primary winding is connected in a delta configuration, and the secondary winding is connected in a Y configuration. This connection is commonly used for distributing power to both three-phase and single-phase loads. The Y connection provides a neutral point for single-phase loads. Thirdly, Y-delta connection. In a Y-delta connection, the primary winding is connected in a Y configuration, and the secondary winding is connected in a delta configuration. This connection is often used for stepping down voltage from a high-voltage transmission system to a lower-voltage distribution system. Fourthly, YY connection. In a YY connection, both the primary and secondary windings are connected in a Y configuration. This connection is simple and economical, but can be susceptible to voltage imbalances and harmonic currents. To mitigate these issues, a tertiary winding is often added to the transformer. The selection of the appropriate three-phase transformer connection depends on the specific application and the requirements of the power system. Factors to consider include voltage levels, load types, voltage regulation, and harmonic content. Understanding the characteristics of different three-phase transformer connections is essential for electrical engineers and technicians.